linger.
So we want to find dy dx.
No way. No. Oh.
I'm like 40 years old and I still get like I just you found my weakness. That kind of humor is like,
Weakness is the fart jokes. It got recorded.
So
Silly old fart jokes.
So y equals ln of x. We're trying to find the derivative of that. I think obviously, but actually I brought this up in the other class, and the question was, wait, what does that dy dx stuff mean again? So let me just take a second on the off chance that we don't know. So we know what this means, right? The blue? Slope, right? Now, that's over an interval. That's an average rate of change. If I reduce the interval, then the slope of the secant gets closer and closer to being a tangent. This is a capital delta. When we talk about over an interval, the slope would be the slope of a secant. But if I reduce that interval, I get closer and closer to being instantaneous. So we use this notation. This is a lowercase delta, but nobody ever wants to write that because that's not fun to write over and over again. It's fun to write once or twice, but writing it repeatedly, it's like, all right, enough of that.
Is that sigma?
That's a lowercase delta.
Oh.
And so as a shorthand way of representing it, we'd write a D instead of the lowercase delta, which is perfectly fine, right? So then the follow-up question was, okay, so that's fine, but what about when I write something like d dx of ln of x? What does that mean? Well, this is my y, particular to whatever situation. So this expression, d dx of ln of x, is the same thing as dy dx, just particular to this y. Right? So the notation, I mean, if you're applying common sense, you come away with the idea that they all mean derivative in some way, shape, or form. It's just a question of in what capacity. But anyway, what we want to do is somehow find the derivative of this without using the limit definition. I happen to know a thing or two about logarithms, and so do you. One thing would be hopefully that ln of x is the same as log base e of x.
Yeah.
All right. That equates to, if I put it in exponential form, I wrote it wrong. E to the y equals x. I psyched myself out there. Then what do we do with that? That is the question. So we do not know the derivative of the natural log, but we do know the derivative of an exponential function. So hopefully we can apply that information or that knowledge here. So let us endeavor. X equals e to the y. I'm gonna I want to write it. It's the same expression, same equation.
It's a very specific.
I want the x on the left-hand side, just so it's in explicit form. But I need to take the derivative of this. It's not going to be dy dx though, because when the function was solved for y in terms of x, we would take the derivative of the y in terms of x. But now it's solved for x in terms of y, so what would be the expression that represents the derivative?
D over dy.
Dx over dy. Everything's reversed, right? We had y in terms of x, which gave us dy dx. Now we have x in terms of y, so roles have been reversed. What is the derivative of e to the y?
E to the y.
E to the y. All right. Now I still need to get dy dx. So
Wait, why is it
Because dy dx happens when you're taking the derivative of your y equation in terms of x. So now we're doing it the other way around, derivative of the x equation in terms of y. All right. So, but I still need to come up with a dy dx, so we can do a little flipperooski here.
Really? There's no flippers?
If you have a proportion, you can flip one side as long as you flip the other side. It's one of those properties that you explored in geometry. You wouldn't think it would happen in geometry, but mean proportional and things like that. You know, those right triangle relationships. Like it comes up in there, but I don't know that you ever generalize it to that. You know, but anyway, I need my answer to be in terms of x. 1 over x. Exactly, and that is because, and I'll highlight it here, or I'll try to, this relationship,
X equals to e to the y.
e to the y and x are the same thing, so everywhere I have an e to the y, I can swap it out for an x. So after all that, we discover that the derivative of the natural log of x is just 1 over x. Which is, I mean, these other kinds of functions, I mean, once we move away from parabolas, lines, and things like that, even like a sine function, you can sort of conceptualize. But once you start moving away from that, it's kind of harder and harder to get a feel for how the slopes work. In this case, we're really looking at a natural log function and what the slopes would be at any point along that natural log function. So I'll do a rough sketch here. This is typically what a natural log function would look like. So if I'm just focusing on this area, for example, okay, that didn't show up. This area, for example, I'm looking at a slope that's steep in the positive direction. All right. Also steep in the positive direction, but not as steep. Now it's starting to get more and more shallow. So these tangent line slopes are getting shallower and shallower as we go. All right. So if I wanted to take a guess at what I thought the slope was here, and these are all just shots in the dark, I might say something like the slope equal to like 10, a rise over run of 10, I don't know. It could be anything, but whatever the second one is has to be smaller than the first one. So maybe the slope here is like 8. Then the third one would have to have a slope, I think probably much less, so maybe like a slope of 4.
Oh, 1 over.
Maybe a slope of like
At least it's close to
1. So it's getting smaller and smaller. That's the moral of the story here. So if I were to graph my derivative function at this location here, I'd have a slope that's pretty high, so I'd plot 10. The second one, it would be a little bit lower. The third one would be a little bit lower. The fourth one would be lower. Fifth one, lower, and so on. And as it turns out, this graph would look something like this. Now, I did that very quickly, and it's not something that I'm going to have you do on this test. So if you're like, well, how the hell am I supposed to do that? You just took like 2 seconds to do it, and now you expect us to do it. That's not what it is. It's just more for to get a sense for a feel of it. We're going to do a whole unit later on, like December, January, where we take time to explore these relationships, like an entire unit to explore this stuff. So this is just a little bit of a taste of it. But really the reason why I'm going over this is so that you understand the importance of doing something like this algebraically or even with your calculator, because the odds of you being able to pick up on some of these relationships just by looking at the original function, it's hit or miss, because you know, if you don't even know what a natural log function looks like to begin with, it's all over. Then, you jazz it up by saying, well, what if I ask you to find the sine of the absolute value of the natural log of x? I don't even know what that looks like. So how are we going to be able to do something like that? It would have to be an analytic approach using the algebra of calculus. Right? So that's a little bit of motivation, a little bit of theory, but hopefully there's something in it for everyone. Anyway, number 8 looks like it would probably be a much more difficult version of number 7, but no, it's not, because pre-calc. Or algebra 2. Okay, I'll allow it. As Miss Hamilton would say, the exponent jumps over the log like a frog. All right, so now that exponent of 4 just became a constant multiple. And we know from just being in the room for the last week or so that assumes that you've been in the room for the last week or so. That all you have to do is take the derivative of the parent function and multiply it by the constant multiple.
I was wrong.
And you get it. 4 over x. Not too bad at all.
So, actually, I'm just going to ask you this outside of this. Remember.
All right, and so we have some other problems on here, but they do sort of follow that idea that if you understand the pre-calculus stuff, so everything that happens before calculus, then you're in pretty good shape. So ln of 5x to the 3rd power. It's like, okay, let's tackle that puppy. Sounds inappropriate. So ln of 5x to the 3rd I just rewrote it, just exaggerating that product there, because sometimes it's not as obvious that there is a product. When you have a product within a logarithm, it tells you to do what? Separate it into what mistake? I don't know what you're talking about. So a product turns into a big old sky. Now I can do the log frog business.
Wait, so that ln5 is close to that? There's no x.
Exactly. So when I go to take the derivative here, the ln of 5 is going to 0 because that's constant. There's no x in there. And then the other part is just like the previous question, where we have a constant multiple multiplied by the derivative of our parent function here. And so our derivative would be 3 over x. All right. I'm hoping that this will be the year that nobody makes this mistake, but historically, I mean, every year is different, but historically, like half the class loses a point on this type of question on the test because they just can't stop themselves. They hop the exponent over the log in that first step. Can't do that. That exponent it does not apply to the 5. 5 is not being raised to that 3rd power. So you have to separate first before you can hop the exponent. If you hop it too early, you got a problem. Okay. So something to keep in mind. Now, in number 10, it's now log base 2, not log base e. So what do? Fortunately, there's a rule that'll handle that. It's a change of base formula. It allows us to convert over from something that's not a base e into something that is base e.
Just a quick question.
Sure.
The last one, why was the ln5 0?
Oh, because it's constant, it doesn't have a variable in it. So the slope of a constant is always 0. And folks, I'm not limiting the use of a calculator. So if you're ever in doubt, go to the calculator, like for example, ln of 5. And you know what? Play it safe. On a test, you know, weird things happen. You lose credit for things that you get right every single other time that you try it. But just because the piece of paper says test on it, now all of a sudden you screw it up. It's just the nature of things sometimes. So put in the original function and put in your y4 and just see what happens. All right. So my y1 gave me a horizontal line. My y4 is giving me also a horizontal line, but specifically at 0. So that's telling me that the derivative is specifically 0. All right, so you can pull it out that way too. All right, and that's going to be even more important when we get through this question, because we're going to have a constant multiple here that's a little crazier. All right, but before we even get to that, we'll use our change of base formula. This is our B. This is our A, following this model. So we're looking at 1 over the natural log of, well, I won't write the B, I'll write it actually as whatever B is. 1 over the natural log of 2 times ln of whatever the A is, x cubed, in this case, over 2. All right, this formula is on the previous page. So if you want to take a look at that, you can, but it's probably worthwhile or worth it to write it down on this page also.
We use this when the base isn't 10 or E?
When it's not E specifically.
E specifically.
Even if it's 10, we still want to use this.
Okay.
We want it natural log. That's the way to go.
All right.
So I have division here. So that's going to become subtraction. Now, that 1 over ln2 is going to apply to each part. So I want to get some parentheses around. I can now do the log frog jumping maneuver. Now this is a big mess, but we can clean it up by distributing. And when we do that, it'll seem like it's a big mess, but it won't be. And just bear in mind that all of that was for the purpose of getting our original function in a more convenient form for us. All right. We haven't done any calculus yet. And I can't tell you how many times I put a problem like this on a test and somebody stops here. And they move on to the next question. They don't even do the calculus part because they figure I've accomplished it enough, you know, like this is a great achievement that I've gotten this far, you know, like don't trip at the finish line. This component here, it's a multiplier of the parent function ln of x. ln of x has a derivative of 1 over x. That coefficient does not have a variable in it. So that makes it a constant multiplier, and that just goes along for the ride. All right, so this is actually a little bit more intimidating of a coefficient than the previous one. ln of 5 is bad enough, but 3 over ln of 2 look crazy.
You lost me in from the third to last step to the second to last step. What'd you factor out?
Oh, I distributed.
Oh, okay.
You lost me.
You
I even knew that.
So,
I'm Caucasian.
the verification part of it. Again, if the idea is in your mind, is this a constant multiple or not, you could always verify it. But in this case, I think you probably want to verify the whole thing and make sure that you didn't just botch the entire derivative up. So how do we do that?
What about is the negative one is negative?
No, it's -1 has a derivative of 0 because it's constant. All right, constant multiples go along to the right, but standalone constants go to 0. All right, so how do we check this? Well, I don't want to have to put my manipulated forms into the calculator, so I want to put the original. So I want to use the log base function, alpha window option 5. And you can type it in as is. Put the fraction alpha y equals n over d. So I could put in the fraction. And it's entirely conceivable that prior to this course, you may never have had need to touch that alpha key before. Now it seems like that's all we're touching. Like the alpha key is so important. Alpha, and then odds are what you're looking for is in that top row. Y equals window, zoom, or trace. All right. So that's my original. Here's what I think the derivative is. 3 over ln2 multiplied by 1 over x. Put that in any way that makes sense to you. That's also equivalent. My y4 is set up. I don't know if a zoom 6 is going to be the best way to go, but I'll give it a shot and I'll adjust it on the fly if I need to. So zoom 6. Checking my work. Original draft. Might run into some domain issues with logs, but we'll deal with that. Alright, so it's tracing over only the positive part. But as long as it's a direct correlation to some part, it's still verifying that the derivative is correct.
ln1.
The reason why it may not be a direct relationship is because natural logs or common logs, any kind of logs, only exist for values that are greater than 0. So this function only exists to the right of the y-axis. So what that's telling me is I can look at the graph, but I don't need to even look at anything to the left of the y-axis. That's irrelevant. Right, so this graph, I mean, we would actually write it as a piecewise, but in this case, all we need is actually just the statement of what the function would be for whatever the relevant values of x's are. Right. So we'll generalize, and we'll keep it simple for this one. The derivative with respect to x. I could take the natural log of x, but I could also have a coefficient. That has a derivative of a over x. We could also have something that's in the form of another type of log. So let's say a times log base b of x. All right, that's where the change of base stuff comes into play. So we would have a 1 over ln b multiplied by, it would be ln of whatever the x is, but that becomes, when you take the derivative, it becomes 1 over x. But then we'd have to multiply by whatever the a value is. I don't really like the second one. I mean, you look at it, you probably don't like it either. But, I mean, the first one's really nice. The second one is like, eh. If you know your change of base formula, you never really need to know the second one, because you could always manipulate your log to begin with to get it to be a natural log, and then go from there. So this one, the first one is necessary. The second one is kind of a luxury. You know, if you have space in your memory banks, then throw it in there. If not, then don't.